if we were to draw a circuit, what does this look like? Draw a diagram. It's a series volt battery connection. It's kind of like saying, I don't know, these are typically like 3-volt batteries. And then ultimately, we've got the bulk filament over here. Why would we put that second battery in there? What does the presence of that second battery do in the circuit?
Increases the current.
Increases the current. By increasing the voltage, it raises the current. By raising the current, it increases the intensity of the bulb. So typically we stack power supplies in series when we want to increase the voltage output. Here's one that's not so obvious though. How do we connect batteries and what's it? I'm not going to say it. I'll just say it this way instead. So here's my load, whatever this is, and here's my battery. I got a 3-volt battery here. And I've got some connection over here. I don't know what this load is, but let's just assume that it's how much current is going to be drawn from that battery? What is I here?
3 amps.
Yeah. Okay. So let's process this for a second. I've got some electrical device, and I need a 3-volt power supply in order to drive this circuit, which implies, if nothing else, that I've got a 3 ampere current draw. I'll tell you what, most batteries cannot drain 3 amperes of current. Certainly not for very damn long. Guess what happens if this battery is only capable of consistently, without overheating, without depleting too quickly, in other words, without chemical reaction limiting the amount of charge it can flow, which will drop the voltage and everything. If this battery can only safely, I'll say, or let's say a 1 amp maximum, what do I do? To get around it? If I add more resistance, now I can't generate all 3 amperes that I need to run the circuit.
And a 2-volt battery going the other direction.
Now I change my voltage, now I change my current. In order to operate at 3 amperes, so now I'm sort of working backwards. I said it was 1 ohm, but now let's say this. Okay, so I've got a 3 amp current need. Whatever this thing is doing, I need 3 amps to run across this thing, the equivalent of 3 volts. How do I do it?
Another battery in parallel.
Put batteries in parallel. And if I put them in parallel and they have the same voltage, they don't affect each other, but what they do, because they'll have the same potential differences across the end, so I'm not going to push current anywhere in. But now I can draw current from this guy, and from this guy, all of whom can generate my 3 amperes I need output. So putting 3 of these in parallel, I can in turn supply 1 amp through each of them, and drive this device without the limitations of just having one battery. Now, this is essentially what happens in a car battery, internally. The term battery means combination of cells. So when you talk about a power cell or a battery cell, that's one little connection. So when you put a bunch of these in series, it's more efficient than just having one big fat cell. So you put a bunch of them in, not in series, in parallel. And when they're in parallel, you draw current from each of them, which limits the chemical reaction barriers. Because you've got 3 different sources of charge or power. You can get a lot. You can get all those 12 amperes or whatever's necessary when you first start that car. That's how you generate that high power output, that high current output very quickly. Now let's think about this. How much power is drawn by each of these batteries? First of all, I'll say, let's put 3 sources in parallel. Now, the power draw through all of them is the net power will be equal to the potential difference across the load, which is where all the work is done. That energy has to be consumed somewhere. And so that's going to be equal to the voltage across this guy. I'll call this V1 times the current, total I. Or if you will, 3 volts times 3 amperes. 9 watts. Joules per coulomb, coulombs per second, joules per second.
The V1 will drop, or just...
V1 is the drop from here to here, which is 3 volts. Because of the connections all being in parallel, it's all 3 volts higher here than it is here. So again, when you add power supplies, one thing that you can do is just put them in parallel together and you just increase capacity without altering voltage. And so you do that when you need more power output from a particular battery. But you don't want to alter the voltage because you don't want to run too much current or too little current through it. So you've got 9 watts of total power requirement, right? This is what your hair dryer or whatever, when you have some electrical appliance, your toaster, your microwave in the back, oh, this is a 5-watt rated appliance. Well, typically what that means, if you've got 120 volts where you're plugging it in, it draws enough current, so 120 times whatever that current is corresponds to 100 watts. Voltage is fixed, but it's a current draw that's related to the power. However, drawing 9 watts out of one battery may not be the best thing to do, because sometimes you use watch batteries, right? Small batteries, because you want high voltages with slow trickling continuous currents, but you don't necessarily want big surge currents. So you use these tiny little watch batteries. But if they aren't capable independently of drawing quite enough current, put 3 of them in parallel together. And that's usually where you see it in watch battery situations. Or small, like CR 125s or 122 batteries, something like that. G25s. So if you can split this into 3 pieces, 3 batteries, as long as each of the individual power supply can generate 3 watts of energy, or can allow the draw of 3 watts, it's just a more efficient way of doing it. That means that the batteries will last longer, if nothing else. because each battery is only going to have so much capacity. Here you go. No way around. Now, is there any questions on that? I mean, I could do like 50,000 of these problems and never do enough of them to satisfy every possible combination. But let's talk for a second about why power supplies tend to be limited. The capacity of a power supply, which is usually rated, a battery, if you will, in watts, it's limited by if it's solid or if it's liquid. Why is it that nails rust very slowly? But if you put like zinc, a chunk of metal in like hydrochloric acid, it bubbles and basically goes away very quickly. What's the difference? Why are they different? Or better yet, why would a chunk of salt, rock salt, when you put it in warm water, say you're making boiling noodles, why would rock salt or chunky salt, when you put it in the water, dissolve slower than if you put granulated salt in the water?
Surface area?
Access. Surface area, mixing, access. So, the more solid state your battery is, the lower the surface area where the chemical reactants have to interact. So you limit the chemical reaction rate, or it's limited by the surface area. Now, if it's a battery like car battery, it's all liquid inside. So you get a more consistent mixing. You increase access of the chemical reacting quantities, and you increase their capacity to chemically react. So when you take rust on a nail, for instance, as it starts to coat, now you decrease the surface area for additional chemical reactions to happen because there's a smaller amount of available iron to interact with the water. There's less there to get to. On the other hand, if you could, as a nail is rusting, scrape the rust off but leave it in the water, it will continually rust at the same rate, as long as you keep removing it and keep removing it and keep removing it. So typically with liquid batteries, as the products are formed, they slough off a little more off the electrodes that are chemically reacting. But when you have solid state batteries, whatever gunk is formed basically coats between them and lowers your capacity for the additional chemical reactions to happen. It's just purely an access issue. But the consequence of it is that if you look inside of a power supply, I'm going to draw my power supply this way. So I've got a power supply, and it's got a positive terminal, and it's got a negative terminal. What's happening inside is driven by two parts. The chemical reaction, which will drive the voltage, the potential difference, and ultimately the amount of charge that is, and the energy of the charge that's being produced. But it's rate limited by the structure of the battery, the surface area of the little reacting elements inside, liquid, solid, all of these factors. And so we refer to that limitation, we call it internal resistance. And it's all built into your battery. So when you get the battery, you get the endpoints. Now here's what's interesting about it. If you attach this, say, to a voltmeter, and what do we know about voltmeters as a general rule? What's optimal for a voltmeter? Remember? High resistance relative to the circuit that you're measuring. Because if it draws too much current, it's going to alter the whole circuit by pushing more current through. And that's going to change the balance of everything. So when you think you're measuring a voltage, like putting any resistor in parallel, now you've screwed with it. So you want the resistance to be high compared to the load of the circuit itself. So if I take a very high resistance voltmeter, and let's give an example. So let's say that this internal resistance, which is just part of the process that is limiting the battery to work as a battery, let's say this is 1 amp or 1 ohm. And I take a voltmeter, I want to measure the voltage. And this voltmeter has a resistance of, say, 100 ohms. What's the voltage across the voltmeter? What is the voltage the voltmeter measures? Calculated in a loop. Basically, I've got, I should put a number in here. Well, let's make it 9 volts. Put in 9 volts. So we've got basically a 9 volt battery attached to this R internal, which is, I'm just hypothetically calling it 1 ohm. And then I'm attaching it to a 100 ohm resistor. So all I'm doing basically is I'm just testing the battery with a voltmeter. What does it measure? Well, what do I know about it? I know there's going to be a certain current across this. And so 9 volts should be equal to the current times 1 ohm, plus the current times 100 ohms. And the current then should be 9 volts divided by 101 ohm. So, again, I probably should have used 5 volts or 10 volts, but I used 9, so we'll figure out what that number is. 0.096 or something, or 0.089. So what voltage corresponds to 0.089 amperes across this voltmeter? And now I know the current across here. How much voltage? So the voltage across the 100 ohms, then, over here, would be 100 times 0.089, or, I write it upside down, 8.9 volts. Okay, so it's an 8.9 volts, almost 9 volts. You say, okay, it's a battery, it's a decent battery. But now, let's say I attach this thing to a very small circuit with a different, instead of this voltmeter, let's attach something else to here and just see what happens. Again, remember, this is the battery. Everything else that's attached is the circuit. Even this little sucker's inside. So, we replace this with some circuit, and that circuit needs a lot of current. This could be like a hairdryer or something. I don't know. Let's say it's a 10 ohm resistor.